All right. What is up, everybody? Tom McGurl here for another episode of the Learn Rust Live series. That's right. We made it pretty far. We started last week. We did a little bit into chapter 17. Today we're going to be finishing up chapter 17. Sorry, my face is looking a little scruffy here. Should have cleaned that up. It's all good. So we started chapter 17. Last time. We're going to finish that up, then we're going to jump into chapter 18 on patterns and matching. Chapter 17 was pretty intense. Doing object-oriented patterns. Again, not my favorite of the, not a big object-oriented, but we saw what those patterns look like in Rust and how you can implement them. We did some stuff with state, so we'll see more of that. All right. As always, the usual plugs. Got to give you the plugs. We got the Twitter.
We have the Twitter. It's a fantastic place. Everyone loves Twitter. Nobody gets kicked off Twitter.
So we got the Twitter. Go here. You'll see when I update live. You'll see when I'm going live. Other updates. So feel free to give that a follow. And then as usual, if you're watching on YouTube or you're catching up on Twitch, you're here on the stream. If you want to catch up on previous episodes that you might have missed, it's all here on the YouTube. So you can find them all here. We have all these parts. We've gone through chapters 1 all the way up to halfway through 17. We've even done the Rustlings exercises. You can find those in the middle here. They started on, So here with part 11, 12, and 13, 14. So 11 through 14, we did the Rustlings exercises. Also some one-off content, Rust development with Docker. More of that to come as I've been talking about, just trying to carve out the right time to do some of that stuff. It's actually more, I guess it's not surprising, but it's more time consuming to do the short videos because they require more editing and prep than me just uploading my stream in a lazy fashion. But yeah, more of that to come. So definitely I enjoyed this, so that was a lot of fun. And then of course the other stuff we did, building a live coding a serverless API with AWS Lambda. Super cool. If you've ever wanted to check out serverless, it's an awesome obviously it's an awesome video. I made it, but it's an awesome intro to doing it. We use Node.js with TypeScript for that, and we use DynamoDB. So if you're looking for a database, a NoSQL database, DynamoDB is great. It's built into Amazon. It works really well with serverless. So that was a fun one. And then before that, we did some React Native stuff, and probably more of that to come, as well as some other stuff. Many of you know I really enjoy other languages and learning new languages, so maybe some more stuff as well. Also, quick note. So some of the comments in YouTube, people have been asking, what are we going to do when we're done with the book? Well, good news. We can do anything, right? So it's kind of like up to us. I know chapter 20 of the book, we're going to build a multi-threaded web server. I would love to see suggestions in the chat and comments on YouTube for suggestions on small apps we can build with Rust. Happy to do that. And otherwise, I'll just look for some small projects and do that. Maybe we'll go through some other Rust materials. The other option is going through some other languages. So as you all know, I'm a huge fan of the Elixir language, so I'd love to put out some content on that, maybe do some live coding with that. But we'll see. The world is our oyster. Well, crab. So we're learning Rust. But yeah, we'll definitely do some stuff with Rust. So we'll build some programs. We'll figure some stuff out, think of some stuff to do, some fun stuff. Maybe we'll make, just some scripts that we would run that can help us out on our machine, maybe some file renaming stuff, whatever, making web requests. We'll figure it out. There's going to be plenty of stuff to do once we've finished the book. We'll have that. We'll be Rustations, right? So we'll have that ability, and we'll take a look at some other Rust projects, and we'll go from there. Try building stuff. We'll see how it goes. We're never going to run out of things to do. So that's the exciting part. All right. Everything we do here is on GitHub. So you have the Learn Rust Live. Pull that down for all the code. I believe I pushed, so I pushed the latest last week, 7 days ago. And as always, got to do it. Got to give a shout out, Steve Klobnik, Carol Nichols, and anyone from the Rust community that's contributed to this book. We couldn't be here without this book, right? This book has been what I've been doing, right? I couldn't be doing this, having fun live coding with all of you every week if it wasn't for this book. So thank you, and huge shout out to Steve Klobnik, Carol Nichols, and anyone from the Rust community that's contributed to this awesome book. Hopefully we can contribute back. So we've gone through the book. We found, I've been taking notes for when we find some areas where it's a little bit odd, or the wording's a little weird, or there could be different examples. So maybe I'll share those notes on a stream, and we can go back and submit some PRs to the book itself. That'd be pretty sweet. So yeah, we'll see where we go. But today, what are we doing? We're going to finish up this part of the object-oriented. So basically the way that this chapter opened up is it presented object-oriented patterns and showed equivalence in Rust. So it's not a one-to-one thing, right? Rust is not an object-oriented programming language per se. In the same way, it's not a functional programming language. It's kind of like a mix of both. There's patterns from both. But it showed you how to implement something in Rust that would be similar to a pattern you would see in object-oriented. And so the thing that we implemented was this blog post. And so if I open up this blog post here, so we started out by building this. And so let's walk through it a little bit. Basically, what we were trying to show is the ability to have, there's a few things we were trying to show, right? So one of the things we were trying to show is how in object-oriented you can have inheritance. Now, while we couldn't have inheritance, what we did have were traits. We can use traits to get similar functionality that we would get from inheritance. The next thing we were trying to show were patterns like private and public functionality. So like in an object-oriented programming language, you probably have methods on an object, some of which you make public to as a public API, and some of which are private. So you can think of like properties, right? You give getters and setters for manipulating properties. And the other thing was, what we did here was we implemented sort of like a state machine. So transitioning a structure into different states and restricting that usage to a public-facing API. And so the cool thing here was we had this post, right? We're dealing with like an object-oriented concept where our object in this case is a post. And our post has a state. And our state is an option. So it could be it could be in none, or it could be in one of these states here. And our state we have is a trait. And so a state can have these functions. And so a state has to implement request review, it should implement approve, and it should implement content. And so it's kind of like saying here that a post, right? A post implements state, right? So you have your state, which it must implement these functions. And so you can say that a post inherits from state, or is a child object of state, in that if anywhere you pass state, you could also pass post. So it's polymorphism, right? Is the concept that we're talking about here. And we learned that in Rust, we're dealing with abstract, what was it? Abstract. Let me search it. Let me search it now because I'm going to forget. Polymorph. Nope, not finding it. But basically, it's a way to get that ability where you define something, you say that it's going to implement these things, and we're leveraging it with structs. So we have our post here, a public function new, that's our constructor. So in object-oriented, you have constructors. We've seen these constructors, it's nothing new. And we create a post with state and some content. And then you have functions for manipulating that interior state, right? So you have add text, which will change our content, a function to get the content, because again, we don't want to just give them access to the content, we have to get it for them. And so the way we do that is we grab our state, unwrap it, and get the content from the state. And then we have request review, which basically gives us the next state. It passes us to the request review state, and approve, which passes us to the approve state. And so we had this other struct called draft, and we're saying that draft implements state, and you have request review and approve for draft as well. So different ways of handling those object-oriented patterns. And here we see pending review and published. So pending review is another one that implements state. So these are like the different states that a post can be in, and they each implement state. So you have published, pending review. So a post can be in the draft state, it can be pending review, or it can be published. So hold on one second. Sorry, 1 second. I have to respond to this. All right, so that's where we ended up. And so where we left off in the book here was this part. Let's go here. We were down here. All right, let's see. We were past this point. We got past this. All right, so here's where we were. So we were thinking about implementing this reject method that changes the post state from pending review back to draft. So let's see. So we have this part here. One downside of the state pattern is that because the states implement the transitions between states, some of the states are coupled to each other. And if we add another state between pending review and published, such as scheduled, we would have to change the code in pending review to transition to scheduled instead. It would be less work if pending review didn't need to change with the addition of the new state, but that would mean switching to another design pattern. So you can see that here. Basically, pending review goes right to published. So if we wanted to implement a state in between here, we'd have to modify this, right, and have it point to the correct state. So there's some modifications there. Another downside is that we've duplicated some logic. To eliminate some of the duplication, we might try to make default implementations for the request review and approve methods on the state trait that returns self. However, this would violate object safety because the trait doesn't know what the concrete self will be exactly. We want to be able to use state as a trait object, so we need its methods to be object safe. So again, let's, because I feel like that's pretty key there. To eliminate some of the duplication, we might try to make default implementations for request review and approve, right? So if you think about this in object-oriented sense, you might have a class that has a method with a default implementation, just in case your thing doesn't implement it, right? So we might try that here. However, this would violate object safety because the trait doesn't know what the concrete self will be exactly. We want to be able to use the state as a trait object, so we need its methods to be object safe. Basically, the self can be one of the many states, and it doesn't know exactly what it is, so that can create weirdness. Other duplication occurs. Other duplication includes the similar implementations of request review and approve method on post. So here, let's take a look at that so we can see what we're talking about. Request review, similar implementation, right? Request review just returns itself. Here it's just returning itself. Here it's different. But you can see there, right? So includes the similar implementations of request review and approve methods on the post. So here's approve, right? And here's request review. They're basically the same code. The difference being that this returns request review and this returns approve, right? So, but similar implementations. Both methods delegate to the implementation of the same method on the value in the state field. So this one's delegating to the approve from its state, right? So it's delegating here. And this one, request review, is delegating to its state. So here and here, right? So it's just, they're both just delegating. So both methods delegate to the, let me just move this so it's out of the way. And I lost my spot now. There we go. Hold on. There we go. All right, perfect. So both methods delegate to the implementation of the same method on the value in the state field of option and set the new value of the state field to the result. If we had a lot of methods on post that followed this pattern, we might consider defining a macro to eliminate the repetition. We're going to learn about that in chapter 19. Pretty cool. By implementing the state pattern exactly as it's defined for object-oriented languages, we're not taking a full advantage of Rust's strengths as we could. Let's look at some changes we can make to the blog crate that can make invalid states and transitions into compile time errors. So this way we'll know up front, right? Encoding states and behaviors as types. We'll show you how to rethink the state pattern to get a different set of trade-offs. Rather than encapsulating the states and transitions completely so outside code has no knowledge of them, we'll encode the states into different types. Consequently, Rust's type checking system will prevent attempts to use draft posts where only published posts are allowed by issuing a compiler error. Again, let's go over that. Rather than encapsulating the states and transitions completely so that outside code has no knowledge of them, so rather than totally encapsulating them in the functions that we're calling so that outside code doesn't know about them, right? We'll encode the states into different types. So we'll use Rust's type system. Consequently, Rust's type checking system will prevent attempts to use draft posts where only published posts are allowed. So we're going to leverage types. What do we mean by doing the transitions in the implementation? Well, that's like here, right? If you look here, when you call request review, we return box new pending review. So we're calling that from here, right? So we're changing the state, and that's internalized. Now we're going to use types for that. So that'll be pretty cool. Let's consider the first part of main in listing 1711. So here we have let mute post equal post new post add text. I ate a salad for lunch today. So let's go there. That's in here. We changed it to post add text. What up Twitch and YouTube? And we assert equal post.content because we don't want to be able to grab the content yet because it's still in draft phase. We'll still enable the creation of new posts in the draft state using post new and the ability to add text to the post content. But instead of having a content method on a draft post that returns an empty string, we'll make it so draft posts don't have the content method at all. That way, if we try to get a draft post content, we'll get a compiler error telling us that the method doesn't exist. As a result, it will be impossible for us to accidentally display draft post content in production because the code won't even compile. So the listing below shows the definition of post struct and a draft post struct, as well as the methods on each. Awesome. All right, so let's implement these here. So we have post, which just has a content string, and draft post, which has content string. So we're gonna modify this here. Pub struct draft post. And then our implementation here, so post function new is gonna return a draft post. And so we create a draft post. And again, don't worry if we're getting rid of this code because it's all gonna be contained in the git commits. So we'll have access to it. And then it turns content string new. And then we're gonna have a public function content. Let's see, are we gonna get rid of this stuff? Yeah, we'll just get rid of it for now. So we're gonna have a new thing here. So we have our public function new. We're gonna have a public function called content, which is gonna take self, and it's gonna return a string slice. And it's gonna return self.content. So it's just grabbing that content, it's just a getter. And then here we have the implementation of draft post. So implement draft post, and that's gonna have a public function called add text. That's gonna take the mutable self, because we're gonna need to change it. It's gonna take text, which is gonna be a string slice, and it's not gonna return anything because it's just gonna mutate self. Self.content.push string, and we're gonna push the text on there. So again, we're just mutating it. That's why it doesn't have a return type there. All right, both the post and draft post structs have a private content field that stores the blog post text. The structs no longer have the state field because we're moving the encoding of the state to the types of the structs. So there's no state field anymore. We're moving the encoding of the state to the types of the structs. So the state is defined by which struct we're using, right? Interesting. The post struct will represent a polished post, and it has content method that returns content. So you can see the post actually has the content, whereas draft post, it's impossible to get content. We still have a post new function, but instead of returning an instance of post, it returns an instance of draft post because content is private and there aren't any functions that return post. It's not possible to create an instance of post right now. So you can see that here. Our new function returns a draft post. It does not return a post itself. There's no way to create that. That's what they're saying. The draft post structs has an add text method, so we can add text to the content as before, but note that the draft post does not have a content method defined. You can't get the content. So now the program ensures all posts start as draft posts, and draft posts don't have their content available for display. Any attempt to get around these constraints will result in a compiler error, so we won't even be able to compile the code. Pretty awesome. Implementing transitions and transformations into different types. So how do we get a published post? We want to enforce the rule that a draft post has to be reviewed and approved before it can be published. A post in the pending review state should still not display any content, right? So if it's pending review, it shouldn't display any content. Let's implement these constraints by adding another struct, pending review post, defining the request review method on draft post to return a pending review post, and defining an approved method on the pending review post to return the post, the final post struct. Okay, so that sounds cool. All right, so first, draft post. We're gonna have a request review, public function, request review. It's gonna take self, and this one's actually gonna return a pending review post, which we haven't defined yet. And that's gonna contain content, and we're just gonna pass on the content from self here, right? Yeah, so I'd say pending review, post, Whoa, why is it? There we go. Uh-oh, I think let's see. Yeah, hold on 1 second. Looks like my AutoHotkey got messed up. Let's fix that. I got my code mode here. No worries, no worries. We'll be back at it in no time. Okay, there we go. Whoa. Okay, hold on. What's going on? What's going on? What's going on? There it is. And let's undo that. So we have pending. I'm in insert mode. I'm like wondering what's going on here. Why is it doing this? Okay, hold on 1 second. It looks like let me try typing without AutoHotkey mode. Okay, there we go, there we go. Yeah, something's messed up with my VS Code. Let's try this again. Okay. And let's see what happens here. Okay, we're good now. I don't know what's going on. That's happened before on stream. It's not new. It's not new. Content. So AutoHotkey is what I use so that I can have my binding similar, because I usually program on a Mac device, and now I'm on Windows. And it also gives me Vim bindings outside of Visual Studio Code, which is really nice if you're used to Vim to be able to use it anywhere. All right, so we have our request review, and we need to implement the pending review post struct. So we can put that right here below. So that's a struct, right? It's a new public struct. It's called pending review post, and it's going to just contain content. And now we need to implement some functions for it. So what functions are going to make? Well, hold on. Let me make sure I'm not in your way here. I'm definitely in your way there. Let me move over here for a second. All right. So we need to implement some functions for it. And so for that, we're going to do implement pending review post. And we're going to implement a function called approve. And already this stuff is a lot easier to understand than what we were doing with the states. I already like this much, much better. Post, and it's going to take the content, and we're just going to pass it our current content. So what's happening here is a lot easier already to understand, in my opinion, right? We have the different states of a post represented, right, by structures. And I would even say we can move, if we wanted to, we can keep all our structs together up top. But I think it's fine. We could probably move this down. But it's nice. What's happening here is you can see that you have a post which has content, a draft post has content, and a pending review post has content. They're the same, but the difference is the implementation, right? So that's why we can't use the same struct for all of them, because we're going to have different implementation blocks. So post only allows creating a new draft post. It also allows getting content. Draft post only allows add text and request review, which returns a pending review post. A pending review post is the only one of the structures that can return a new post object, right? Even post new just returns a draft post. So here we get the final post, and along the way you can see when we transition from one state to another, we're just passing on the content, right? So pretty easy. All right, I like it. The request review and approve methods take ownership of self, thus consuming the draft post and pending review post instances and transforming them into pending review post and published post, respectively. That way, we don't have any lingering draft post instances that we've called request review on. So what we're saying here is request review and approve, they take ownership of self. So self can't be used outside those blocks, right? So it's actually moving ownership of that thing, which is great, because that's why, you can see here, we're just taking self directly. We're not taking a reference to self. We're actually taking ownership. And that's so we don't leave, like they mentioned here, we don't leave lingering draft posts around, which is really cool. So after we've called request review on them, they're cleaned up, right? The pending review post struct doesn't have a content method defined on it. So attempting to read its content results in a compiler error, which is what we want, as with the draft post. So pending review, you can't get the content. There's no function for that, right? Pending review just says approve. Draft post doesn't have content. The only one that has content is the final one, which is what we want. We only want to be able to get the content from the final post. Because the only way to get a published post instance that does not have content method defined is to call the approve method on the pending review post, and the only way to get a pending review post is to call the request review method on draft post. We've now encoded the blog post workflow into the type system. This is much cleaner in my opinion. I like this a lot better than what we had before. But we also have to make some small changes to main. The request review and approve methods return new instances rather than modifying the struct they're called on. So we need to add more let post shadowing assignments to save the returned instances. Remember shadowing, right? It's when you can use the let keyword again, and it'll actually allow you to change the type of a variable. We also can have the assertions about the draft and pending review post contents be empty strings, nor do we need them. And we can compile code that tries to use the content of posts in those states any longer. The updated code in main is shown below. So we got to update our main. So we have our mutable post, which is a post new, which again is going to return a draft post. You can see that right here. How cool is that? How cool is that? Come on. And then we're going to add some text. I'm going to add the text. What up, Twitch and YouTube? You can see we can't get the content from a post, right? So what we're going to need to do is we're going to do post. So we're going to, this is the shadowing, right? Post, we're going to change the type here. Post.requestReview. And it's going to show us right away what it's returning. It's returning a pending review post. And then we're going to take that version of post and we're going to say post equals post.approve. And you can see that we finally get an actual post. And now calling post.content is totally fine. And so here we should say we want to assert equal post.content should be equal to, oh no. Yeah, there we go. Assert equal post.content post. So now if we run this, get out of your way. Our assertion is good. Actually, I have to run cargo test, right? Cargo test. But yep, we're good. Everything works as expected. So pretty cool. The changes we needed to make to main to reassign posts mean that this implementation doesn't quite follow the object-oriented state pattern anymore. The transformations between the states are no longer encapsulated entirely within the post implementation. However, our gain is that invalid states are now impossible because of the type system and the type checking that happens at compile time. This ensures that certain bugs, such as display of the content of an unpublished post, will be discovered before they can make it in production. They'll be discovered before you can deliver your code, right? They're going to be discovered while you're working on your code. That's the beauty of having a compiled language. Try the task suggested for additional requirements that we mentioned at the start of this section on the blog crate, as it is after listing 1720, to see what you think about the design of this version of the code. Note that some of the tasks might be completed already in this design. We've seen that even though Rust is capable of implementing object-oriented design patterns, other patterns, such as encoding state into the type system, are also available in Rust. These patterns have different trade-offs. Although you might be very familiar with object-oriented patterns, rethinking the problem to take advantage of Rust features can provide benefits such as preventing some bugs at compile time. Object-oriented patterns won't always be the best solution in Rust due to certain features like ownership that object-oriented languages don't have. True. Let's do that. Let's do what they said. So they want us to implement this, and that's, I low-key skipped it because I knew we were going to do this. Where is it? This part here where we want to implement. Let me just search for it. So we want to add a reject method that changes the post state from pending review back to draft. So let's look at how we would do that. So pending review post, right? We want to go from a pending review post back to a draft post. So how can we do that? Well, we need a function called reject. That's going to take self. We're going to want to take ownership here again. And what is it going to return? It's going to return a draft post, right? So again, it's called reject because from a draft post, you'll request review. Someone can reject that pending review and it'll go back to a draft. So draft post, and this makes it a lot easier. We're going to just create a draft post. And what do we do? We're just going to set the content of that draft post equal to self.content. So now our draft post can go back into reject mode. Require 2 calls to approve before the state can be changed to publish. So that's interesting. Require 2 calls to approve before the state can be changed to published. So in our case, a published draft is just a post. We've learned about this a little bit, where we can actually encapsulate the number of calls, right? We did this with our memoization. So we could, let's think about how we can do this. So we've done this a little bit with the memoization. So what we can do is we can add to our pending review post how many approvals it has. So we could say approvals, and that'll be equal to an assigned 32-bit integer. Or let's do unsigned. Has to be positive, right? And when we create a pending review post, we'll default to having 0 approvals, right? Now, when we approve, we'll want to do, well, first we'll need a way to update the approval. And so that's the way we'll do that, is when we approve. When we approve, what we'll want to do is we'll want to check for how many approvals we have. If we have 1, we'll progress it into a post, because that'll mean this is the second approval. If we have 0, we'll increase the approvals to 1. So what we can do is we can do match. Well, we don't need to match. We can just do a basic if here. If self dot. Well, we actually probably want a way to get approval, so we can. Actually, I guess we don't want to expose it to. Yeah, we don't need to expose the number of approvals. So what we'll do is we'll just do approvals. Equals 1, right? Then we'll return the post. So if we have 1 approval, we'll return the post. Otherwise, we'll return, and we'll try this, and then we'll try to use a pattern here. Otherwise, what we'll do is we'll say so. This is a key thing here. We need to mutate approvals, right? So if we want to mutate approvals, we're going to need a function to do that, right? Because we're going to need to pass it a reference to self, right? Because here we have the actual, we've moved self. So what we'll do is we'll create a private function. So we'll just call it function increase approvals, and what that's going to do is that's going to take the mutable self, right, and it's going to do nothing. It's a void function, but what it will do is it will do self dot approvals plus equals 1. Okay, so we made it private because we don't want to expose this. We want to just have this be done when we approve. And so here what we'll do is we will call increase self dot increase approvals. And we probably have to pass it. All right, let's see what it says. It'll tell us. Mismatch types, expected struct post found a unit type. That's because we're supposed to return a post. So here, this is key here. So here, it may return a post, but it might not return a post, because it will only return a post if it's got 2 approvals. So if it doesn't have 2 approvals, it should return a pending review post. So what do we do here? Well, we can specify that approve will either return a pending review post or a regular post. How are we going to do that? Let's see. I'm thinking about how we can do that. So we basically want something that implements, we don't have a trait definition here. We're not using state anymore. In fact, let's get rid of this stuff. We don't need any of this stuff. Okay, so we want to return a post if required 2 calls to approve before the state can be changed to published. So yeah, we only want to return a post if there's been 2 approvals. So I'm wondering if we can do something with a pattern here. Let's see. let's see if we can just basically say that it'd be nice to be able to say that approve can return a type of post or a type of pending review post by basically declaring that both of these implement a particular trait. That's one way we can do it, right? Because we can say that a function returns something that implements a particular trait. Trying to think if there's another way to do this, to handle this. Let me think. This also has to change, I realize. But here, for now, to get this to stop complaining, let me just return a post. This is incorrect, but let's just return it anyway. Because I want to see how we can call this here. All right, cannot borrow self as mutable. So approve needs to take, I guess in this case, approve needs to take the, we could have two approvals. Let's see. Approve can, yeah, you know what we can do? Create some indirection. I really just want approve right now to increase the approvals. Let's start with that, and then we'll figure out how to return the post. So for now, let's have approve just simply takes the mutable self and just calls, right now we're just going to delegate to increase approvals. Right? And so what we can do is we can change this to return a option, right? So you can have post or none. I think that could work. Let's see what that looks like. We'll have to mess with the API a bit, but what that would basically mean is when you call approve on a post, you might get something or you might get nothing. We really want to make sure that you actually get back the let's play with it. Because what I'm thinking is if you call approve, you still want to have the post, right? So you don't want to get back none. That'd be an awkward API. But let's start with that just because that's probably a little bit easier to handle. So we'll do option. And so we'll increase approvals. And so if self.approvals equals 2, right? Then we can return some post, else none. And here we need to do some post, and we'll construct content equal to self.content. And again, the weird thing here is that we're taking the mutable self, and so here it's awkward because we cannot move. So it says here, cannot move out of self-content, which is behind a mutable reference. Move occurs because self-content has type standard string, which doesn't implement the copy trait. So we'd have to do, that'll give us, that won't work. Okay. So yeah, this is an interesting one. I feel like approve, we know we want to increase the approvals. And we probably want to, yeah, we know we want to increase the approvals. Now I'm trying to think how best to handle returning a pending review post or a post. Let's see. Nothing interesting there. Okay, so let's increase approvals. We definitely need. But the problem is we can't return a new post because we would need to take self here, right? We don't want to take it mutable because we want to move it. We want to move the content. So I'm wondering if I don't think there's a way to pattern match in the arguments. That would be sweet, but I don't think there's a way to do that. So I'm thinking if approve has to have a defined API, approve essentially needs to return either a pending review post or a post. So we definitely, I think, need to create a trait for those to mark them as similar, right? That's the only way I can think to do it. And we can say that it has to return something that implements content. Let me see something. Let's see what we were doing before, where we had our trait state. This just said that they had to implement a function called request review. In our case, they just have to implement a function called, well, actually, they don't have any functions in common, right? That's the weird thing. So let's see. We could return. Wait, let's go back to just how we had it with the post and let's rethink this. So approve if approvals equals 2, let's do it, just to make it clear. We're going to return a post. Else, we're going to return self. And we need to increase approvals. This is interesting. I'm not sure how to handle this. We might have to come back to this. Function approve, self. So we definitely need to keep track of approvals. I'm wondering if it makes sense to keep track of approvals here. Feels like it does. Right? We have our number of approvals. You call approve, because that's the API we want, right? We want to be able to call approve. And we want to post if the approvals equals 2. Otherwise, we want to return the pending review post. We want to have no action, essentially. So we basically want to do something like pending review post contents self.content. But we also need to manipulate the approvals, but also it's going to be a mismatch type. So we could do something really silly where it's like not 2 calls to approve. Let me see, did it actually mention that it needs to be 2 calls, require 2 calls to approve for the state can be changed? So I feel like that might be easier to do with the states that we had before. I'm not totally sure. Feels a little more difficult. Let's see what it says down here. Try the task suggested for additional requirements that we mentioned at the start of this section. Note that some of the tasks might be completed already in this design. Yeah, I'm not totally sure how to... Oh, you know what we could do? You know what we could do? We can implement it with... I know what we can do. We can implement it with a separate thing. So a separate struct, right? Because we want to model it as a separate state, piece of state. So what we can do is we can have pending review post with approve that simply returns... I have an idea. Okay. So here, let's check this out. We'll get rid of approvals. We're going to have another struct here. Pending first review post. Pub struct pending second review post. And it's also going to have content, right? And so we're just going to transition. So pending review post, when you call approve, is just going to return... Check this out. What the hell? Sorry, I don't know why my indent's wrong. Yeah, I like this. Okay, so this one will return a... This will be pending first review post. Or we can keep calling this pending review post, just so we don't have to change all these other spots. So pending review post will return a pending second review post, right? And so what we can do is reject can go back to Draftpost. That's fine. We're gonna have a little bit of code duplication, but we can clean that up. We can get rid of this. And then we're gonna have another implementation block. What does this say? No field approvals. Oh, we gotta save probably. Duplicate definition with name approve. Oh, because I have to do this. I have to fix this. So this one will be pending second review post. And when you call approve on that, that's going to return a post. It's going to have a reject, which will go back to, well, reject can go back to the first review. It should probably go back to a draft, though. I think it makes more sense to have it go back to a draft. Oh, product requirements, right? Who knows? Okay, so now basically the flow is when you go from a draft to pending review. When you approve a pending review post, it transitions to a pending second review post. When you approve that, it returns a post. So there's duplication. These are very similar blocks of code, but it better maps the state transition, and we didn't have to keep track of things, right? So let's try that out. Let's test it. So post.approve, we want to assert equal initially that we get nothing because it requires 2 approvals. Right, so we should get nothing the first time. So I'll put that here. First approval. Second approval. And then we should actually get the content, right? What does this want? No method name content found for struct pending second review post. See, we can't get the content, which is great. So it's giving us the issue at compile time. This is fantastic. This is what we wanted, right? We didn't have that before. So now we know at compile time, hey, you're not gonna be able to get this because you've only approved it once. So let's go ahead and get rid of that. And here, we also need to approve again. Approve again. And look, it shows you the states. Look at how cool this is. Let me zoom in so you all can see how cool this is. This is pretty cool. I think this is pretty cool. So this, by the way, you may be asking, Tom, how did you get those awesome things to show up in your editor? Well, I'm using Rust Analyzer. Gray Jack showed up one day in the chat. He came in hot with some dragon energy. And he said, you got to check out Rust Analyzer. And on top of that, you got to check out my theme. So what do? We pulled it in. Where is it? How do you spell gray? Gray Jack. We pulled it in. We're like, of course we're going to check that out. And we got these awesome, Rust Analyzer gives us this. So we can see that this post starts out as a pending review post, right? We call request review. Or sorry, it starts out as a draft post. We call request review. We get a pending review post. The result of this is a pending second review post. And the result of this is a post. It's pretty neat, right? And why can it do this? Because we're using a compiled language that it does some inference up ahead. And the compiler is running, right? The compiler is running. In my case with Rust Analyzer, it runs all the time and runs cargo check. But how cool is this? I don't know. I think it's pretty sweet. All right. We're good there. Let's check out the summary. We're done. We're moving on to the next chapter. Who's ready? What time is it? We're good. We're good. Summary. No matter whether or not you think Rust is an object-oriented language after reading this chapter, you now know that you can use trait objects to get some object-oriented features in Rust. Dynamic dispatch can give your code some flexibility in exchange for a bit of runtime performance. That's key. In exchange for a bit of runtime performance, right? You can use this flexibility to implement object-oriented patterns that can help your code's maintainability. Rust also has other features like ownership that object-oriented languages do not have. An object-oriented pattern won't always be the best way to take advantage of Rust's strengths, but it's an available option. Next, we're going to look at patterns, which are another of Rust features that enable lots of flexibility. We looked at them briefly throughout the book, but haven't seen their full capability yet. So patterns, we're talking about pattern matching. Remember we matched on option, right? If it's some and the type or none. Pattern matching is, I love it. I know Albert in the chat loves it because he's writing Elixir with me and we have pattern matching and it is like, it's the big leagues. Once you have that, you're like feeling empowered. You're like, oh, recursion's easy. Things are easy. They make sense. So I'm excited to see what we can do with Rust in terms of patterns. All right. That wraps it. Next chapter. Patterns and matching. Who would have thought? Who would have thought we'd make it all the way? We're going to make it through the whole book. We're on chapter 18 already. It's been a long journey, but it's been fun. Let's continue. Patterns and matching. Patterns are a special syntax in Rust for matching against the structure of types, both complex and simple. Using patterns in conjunction with match expressions and other constructs gives you more control over a program's control flow. A pattern consists of some combination of the following: literals, destructured arrays, enums, structured tuples. You remember the destructuring, right? Where you could have a point, a structure called point, and you can say let xy equal point, right? If it had an xy property. Variables, wildcards, and placeholders. So these are the things we can pattern match on, right? Literals, destructured arrays, enums, structured tuples, variables, wildcards, and placeholders. These components describe the shape of the data we're working with, which, when we match against values to determine whether our program has the correct data to continue running a particular piece of code. So these describe the shapes which we then match with, right? And we use that match to run a particular arm, as we've called it, of the code. To use a pattern, we compare it to some value. In the pattern matching, if the pattern matches the value, we use the value parts in our code. Recall the match expression in chapter 6 that used patterns such as the coin sorting machine example. We can pull that up. Let's pull it up. Got like my little Rivendell background there. Very nerdy, very cool. All right, so they said chapter 6, right? So let's go back. Let's go to chapter 6. That's why we labeled everything like this. Do we not have chapter 6? Come on. When did we start doing the chapters? Come on, what's going on here? Let's see, what do we got here? What do we got? I guess we didn't start doing the chapters till 9, but we have coins. That's what we're actually looking for. Let's see what that looks like. So here's a little pattern matching. So here's some pattern matching. Value in cents, match coin. If the coin is of type penny, remember we were using an enum here. We're matching on the enum. If coin penny, do this. If coin nickel, do that. If coin dime, do that. If coin quarter, do that. So that's pattern matching using an enum, right? Pretty cool. This chapter is a reference on all things related to patterns. We'll cover the valid places to use patterns, the difference between refutable and irrefutable patterns, and the different kinds of pattern syntax that you might see. By the end of the chapter, you'll know how to use patterns to express many concepts in a clear way. I'm ready. Hope you're ready. All right. All the places patterns can be used. Ooh, I want to make... Okay, good. We're going to do some coding. All right, so I'm going to do... let's kind of... Yeah, let's just make a new chapter 18. So I'm going to do make directory chapter 18. Patterns and matching. Perfect. I'm going to go into there and I'm going to create a project. Oh, I accidentally created this in coins. Hold on. Let's move up a level. There we go. Chapter 18, patterns and matching. And I'm going to do cargo new. We'll call it places patterns can be used. Let's call it places patterns can be used. Easy enough, right? And let's go ahead and open that. That's going to give us that main file, right? There we go. Now we can mess around if we need to. Perfect. Patterns pop up in a number of places in Rust. Whew. Little alliteration. Patterns pop up in a number of places in Rust. Patterns pop up in a number of places in Rust. And you've been using them a lot without realizing it. This section discusses all the places where patterns are valid. Match arms. As discussed in chapter 6, we use patterns in the arm of match expressions. Formally, match expressions are defined as the keyword match and a value to match on, and one or more match arms that consist of a pattern and an expression to run if the value matches that arm's pattern, like this. Match value, if it matches this, it'll run this, otherwise it'll run this, and we call these arms. Why do we call them arms? I don't know, some people call them branches in other languages. We call them arms here. One requirement for match expressions is that they need to be exhaustive, in the sense that all possibilities for the value in the match expression must be accounted for. One way to ensure you've covered every possibility is to have a catch-all pattern for the last arm. For example, a variable name matching any value can never fail and thus cover every remaining case. So at the end, you have like a default, right? If you've used a switch case, right? If you use a switch case in JavaScript or something like that in Python, that's not quite pattern matching because it's not actually matching on values. You have to you actually have to set the case yourself. So it's kind of like that with like a default branch, but it's a different concept in that it's actually can match on the actual values. Whereas with a switch case, right, you have to say, given this value, if it equals this, equals this. So similar. In chapter 6, we discussed how to use if let. Oh, wait, here. I forgot about this. A particular pattern, underscore, will match anything, but it never binds to a variable. So it's often used in the last match arm. The underscore pattern can be useful when you want to ignore a value not specified. For example, we'll cover the underscore pattern in more detail in the ignoring values in a pattern section later in this chapter. All right, conditional if expressions. In chapter 6, we discussed how to use if let expressions mainly as a shorter way to write the equivalent of a match. That only matches one case. Optionally, if let can have a corresponding else containing code to run if the pattern in the if let doesn't match. So if it fails to match that, you can give it some other code to run. In the listing below, we see that it's possible to mix and match if let, else if let expressions. Doing so gives us more flexibility than a match expression in which we can express only one value to compare the patterns. Also, the conditions in a series of if let, else if, and else if let arms aren't required to relate to each other. Like they don't have to operate on the same value, right? They could be totally different conditionals. The code in the listing below shows a series of checks for several conditions that decide what the background color should be. For this example, we've created variables with hard-coded values that a real program might receive from user input. Okay, I'll write it up. So always can use the practice typing here. So we have favorite color, which is going to be an option, right? An option that either may contain a string slice or it will contain none. We're going to default that to none. All right. We're going to have a is Tuesday. It is. It actually is Tuesday. So we're going to set that to true. We're going to have an age, which is going to be a result of an unsigned 8-bit integer or something else equals, and why are we using a result? Because we're trying to parse a string, and the string might not successfully parse. So that's why. We don't care about the none type. We only care if it's present. So the result is basically if it's okay, we'll give you this. If there's an error, we'll give you, doesn't matter. So it's basically saying we don't care about the error from the parse. All right, if let some color equal favorite color. What does this mean? Basically it's saying if favorite color contains a color, right? If let some color, favorite color, it's going to store the result of that in a variable. So favorite color returns a sum with a string slice. It's going to store that in the variable color. And then what are we going to do? We're going to say print ln using your favorite color, comma, has the background, and we're passing it color. All right. And then we have an else if here. Else if is Tuesday. So you can see they're not related, right? This branch is based off of the favorite color. This is based off of it's Tuesday. In our case, it is Tuesday. It's Tuesday night, so you know where you're at. You're on the stream, Tom and Girl stream, all one of you. I'm just kidding, but not really. All right, print ln. Tuesday is Green Day. Is it? Tuesday is stream day. I can't even spell day. All right, Tuesday is stream day. Why do I have this extra thing here? I don't know. Let's get rid of it. Otherwise, else if let, and remember if let is going to say it's the same thing as if let above, but it's just in an else if. So what we're saying is if age returns an actual age, capture that as the variable age there. And so we're going to do here another more nested ifs. If age is greater than 30, it's not, I'm 30, relax. Exactly 30. What do I look like? Using purple as the background color. Else, I'm going to just copy this because I don't feel like typing it because it's just the same stuff. Else we're going to use orange, right? I like orange. That's my favorite color. You can see the orange touches. We have orange and purple touches, right, in this stream. We like both those colors. And then otherwise, we're going to print using blue as a background color. So let's walk through this one step at a time. All right. So if favorite color yields a value, some color, we're going to store that in color. We're going to print that out. If it's Tuesday, we're going to print out Tuesday is stream day. If age yields an age, right? Okay, meaning if it's able to parse and it yields an age, if it's greater than 30, we're going to print using purple as a background color. Otherwise, we're going to print orange. If the age does not successfully yield an age, so in any other case that parse fails, we're going to say using blue as the background color. If the user specifies a favorite color, the color is the background color. Okay, so we just went through this, so I'm going to skip this. The conditional structure lets us support complex requirements. So this is like business logic, right? This is the kind of thing you would definitely want to unit test. And if you are not, you are a fool. You can see that the if-let, the conditional structure lets us support complex requirements with the hard-coded values we have here. The example will print using purple as the background color. Well, let's see. Why will it do that? Well, because age will yield age. This one runs last. Well, in this case, it'll yield Tuesday as stream day because we marked that as true, right? But if it wasn't Tuesday, it would yield age. This should successfully parse, returning 34, and so then it should give us purple, which makes sense. You can see that if-let can also introduce shadowed variables in the same way that match arms can. The line if-let OK age equals age introduces a new shadowed age variable that contains the value inside the OK variant. This means we need to place the if age greater than 30 condition within the block. We can't combine these two conditions into if-let OK age equals age and age greater than 30. The shadowed age we want to compare to 30 isn't valid until the new scope starts with the curly bracket. What do we mean by that? Well, the way that this works is an if-let, whatever is here, whatever gets constructed here is only available inside the block. Here, age is actually referring to the age captured here. This is a shadowing that is occurring. Because remember, if you look at what age is, well, age is declared up here. This is shadowing age, redefining it, and allowing it to be used within this block. That's what's happening there. So, pretty cool. The downside of using if-let expressions is that the compiler doesn't check exhaustiveness. What do I mean by that? It doesn't check that we've handled all the conditions. You can clearly see here we haven't handled the condition in which favorite color is none. It's just going to not go to that first branch or first arm, right? Whereas the match expression would handle exhaustiveness. If we omitted the last else block and therefore mishandling some cases, the compiler would not alert us to the possible bug. So if we didn't have this fallback, we could run into an issue where none of these branches trigger, right? While-let condition loops. Similar in construction to if-let, the while-let conditional loop allows a while loop to run for as long as a pattern continues to match. The example in the listing below shows a while-let loop that uses a vector as a stack and prints the values in the vector in the opposite order in which they were pushed. So again, push it, it's going to print in the opposite order. So let's write that out. Let mutable stack equals vector new. Stack.push 1. We're going to push 1. Push 2, and then while let's sum. So while that vector, basically what this is saying is while that vector is still yielding values, right, we're going to try to pop it off. So while popping off the stack still yields values, we're going to go ahead and print those values. and we're going to capture them at top. Now what we're not handling is the case where it's none. All that means is when this yields none, it's going to return, it's going to be finished, right? As soon as stacked up pop, which returns an option, right? As soon as this returns none, this will no longer be true, and we'll be done there. All right, cool. The example prints 3, 2, then 1. Let's try it out. Get out of your way. Oh, am I in the right project? 3, 2, 1. There you go. Oh, all right. The example prints out 3, 2, then 1. The pop method takes the last element out of the vector and returns some value. If the vector is empty, pop returns none. The while loop continues running the code in its block as long as pop returns some. When pop returns none, the loop stops. We can't use while let to pop every element. We can use while let to pop every element off of our stack. For loops. In chapter 3, we mentioned that the for loop is the most common loop structure in Rust, but we haven't yet discussed the pattern that for takes. In a for loop, the pattern is the value that directly follows the keyword for. So in for x in y, the x is the pattern. So the listing below demonstrates how to use a pattern in a for loop to destructure or break apart a tuple as part of the for loop. Let's do that. So let's move this down here. Let v, and we're going to use the vector macro a, b, c. All right. And let's do for index. So here we're destructuring value in v.iter, iterating over it and enumerating it. Enumerating it is going to give it the index, right? So enumerating it takes a, let me see if we can find it here. Yeah, so it takes a value, right? And it's going to append the index to it. So that's what, iter will just give us the value, right? So this is what's going to enumerate the value with the index. And that's how we're able to pull out that from this tuple, because enumerate returns a tuple, you can see here. Enumerate itself, where size. The iterator returned yields pairs I value. Pretty cool. All right, so index value from enumerate. And what we're going to do is we're going to print ln is at index. And we're just going to template these in, value, comma, index. And let's try printing that. Move out of your way. A is at index 0, B is at 1, and C is at 2. Awesome. Very easy and straightforward. We use the enumerate method to adapt an iterator to produce a value, and that value's index of that iterator, placed into a tuple. The first value produced is the tuple 0a. When this value is matched in the pattern index value, index will be 0 and value will be a, printing the first line to the output. So pretty cool. Let statements. Prior to this chapter, we had only explicitly discussed using patterns with match and if let, but in fact, we've used patterns in other places as well, including the let statements. For example, consider this straightforward variable assignment with let. I bet we're about to find out that it works like Elixir and that it's actually not assignment. I knew it. I knew it. Throughout this book, we've used let like this hundreds of times. Hundreds. And although you might not have realized it, you were using patterns. More formally, a let statement looks like this. Pattern expression. I knew it. In statements like x equals 5, with a variable name in the pattern slot, the variable name is just a particularly simple form of a pattern. Rust compares the expression against the pattern and assigns any names it finds. So in the let x equals find example, x is a pattern that means bind what matches here to the variable x. Because the name x is the whole pattern, this pattern effectively means bind everything to the variable x, whatever the value is. To see this pattern matching aspect of let more clearly, consider the listing below, which uses a pattern with let to destructure a tuple. That's awesome. So yeah, this works a lot like Elixir, which is another language that has this concept. Equals 1, 2, 3. So pretty cool. Here, we match a tuple against a pattern. Rust compares the value 1, 2, 3 to the pattern x, y, z and sees that the value matches the pattern. So Rust binds 1 to x, 2 to y, and 3 to z. You can think of this tuple pattern as nesting 3 individual variable patterns inside it. If the number of elements in the pattern doesn't match the number of elements in the tuple, then overall type won't match and we'll get a compiler error. So the type won't match. You can't match a 2-length tuple to a 3-length, right? For example, the listing below shows an attempt to destructure a tuple with 3 elements into 2 variables, which won't work. What we could do, though, is we could do this. If we had something like this, I'm just going to do 4, 5, 6, and I'm going to change these to Z and W. If we did have something like this, we could make this work. You'll see here it's not going to like it. Actually, it's not complaining. Oh, I had to save. So it doesn't like it. But what we could do is we could say, okay, we'll take that third variable. We just don't care about it. So we'll mark it like that. And now this is successfully matching, and it's no problem. So pretty cool. If we want to ignore one or more values in the tuple, we could use the underscore or dot dot, as you'll see in ignoring. We can try to use dot dot as well. If the problem is that we have too many variables in the pattern, the solution is to make the types match by removing variables so that the number of variables equals the number of elements in the tuple. Function parameters. So, maybe we can do pattern matching here a little bit. Function parameters can also be patterns. The listing 18.6, which declares a function named foo that takes on one parameter named x, a type signed 32-bit integer, should now look familiar. Foo x, we've seen that, right? We can print that. Foo takes x of signed 32-bit integer, that's all. The x part is a pattern. As we did with let, we could match a tuple in a function's arguments to the pattern. The listing below splits the values in a tuple as we pass it to a function. So this is like destructuring in JavaScript, right? Or quargs kind of in Python, right? Where you can take a bunch of different things and destructure in the arguments. So I'm going to say function print coordinates. It's going to take a mutable x, y, and it's going to get that from the type that this function supports, which is a signed 32-bit integer and a signed 32-bit integer. And we're just going to print ln current location, and we'll just print that out. X comma y. And here we'll do let point equal 3 comma 5. Do the same thing there. We have print coordinates, and we'll pass it a reference to that point. This code prints current location 3, 5. The values 3, 5 match the pattern x, y, and so x is the value 3 and y is the value 5. We can also use patterns in closure parameter lists in the same way as in function parameter lists, because closures are similar to functions as discussed in chapter 13. At this point, you see several ways of using patterns, but patterns don't work the same in every place we can use them. In some places, the patterns must be irrefutable. In other circumstances, they can be refutable. We'll discuss these two concepts next. Cool. Refutability, whether a pattern might fail to match. Patterns come in two forms, refutable and irrefutable. Patterns that will match any possible value passed are irrefutable. An example would be x is x in the following statement, x equals 5. Because x matches anything and therefore cannot fail to match, patterns that can fail to match for some possible reason are refutable. So this first example is irrefutable. It will always match. But if they can fail to match, they are refutable. An example would be sum x in the expression if let sum x a value. Because if the value a value, that's weird to say, but if the value a underscore value variable is none rather than sum, then the sum x won't match. So it's a refutable pattern match there. Function parameters, let statements, and for loops can only accept irrefutable patterns because the program cannot do anything meaningful when values don't match. So they need to be irrefutable, right? It needs to be exhaustive. It needs to make sure everything's handled. The if, let, and while let expressions accept refutable and irrefutable patterns, but the compiler warns against irrefutable patterns because by definition, they're intended to handle possible failure. The functionality of a conditional is in its ability to perform different depending on success or failure. In general, you shouldn't have to worry about the distinction between refutable and irrefutable patterns. However, you do need to be familiar with the concept of refutability so you can respond when you see it in the error message. In those cases, you'll need to change either the pattern or the construct you're using the pattern with, depending on the intended behavior of the code. Let's look at an example of what happens when we try to use a refutable pattern where Rust requires an irrefutable pattern and vice versa. Listing 18.8 shows a let statement, but for the pattern we've specified some x, a refutable pattern, as you might expect, the code will not compile. So here we have some x, some option value. If some option value has none value, it would fail. So that's why you can't do this, right? You need to handle that none case. However, the let statement can only accept an irrefutable pattern because there's nothing valid the code can do with a none value. And that's why we don't do this, right? We would use an if let. To fix the problem where we have a refutable pattern where an irrefutable pattern is needed, we can change the code that uses the pattern. Instead of using let, we can use if let. Then if the pattern doesn't match, the code will just skip that code in the curly brackets, giving it a way to continue in a valid way, right? We've given the code an out. The code is perfectly valid, although it means we cannot use an irrefutable pattern without receiving an error. If we give if let a pattern that will always match, such as x, as shown in the listing below, the compiler will give a warning, let x equal 5. So this is always going to be the case. Rust complains that it doesn't make sense to use if let with an irrefutable pattern. For this reason, match arms must use refutable patterns, except for the last arm, which should match anything, basically should match any remaining values with an irrefutable pattern. Rust allows us to use an irrefutable pattern in a match with only one arm, but this syntax isn't particularly useful and could be replaced with a simpler let statement. Now that you know when to use patterns and the difference between refutable and irrefutable patterns, let's cover all the syntax we can use to create patterns. Pattern syntax. Throughout the book, you see examples of many kinds of patterns. In this section, we gather all the syntax valid in patterns and discuss why you might want to use each one. So matching literals. As you saw in Chapter 6, you can match patterns against literals directly. The following code gives some examples. Oh, so here's what we'll do. I will do let's do another project here. We'll call it pattern syntax. All right, and we will open pattern syntax. And what I'm going to do here is I'm just going to create a different little function for each of these. So we'll have our main there, but then we'll have a function called matching literals. And so we'll do let x equal, so this is irrefutable, right? That's what we noticed. We saw that, learned that, right? And then we're going to match on x, match x. If it's 1, it'll print ln 1, right? We're just going to write, you get the picture, so we're just going to write this. Otherwise, and this is the catch-all happens here. Right? So this code prints 1 because the value of x is 1. The syntax is useful when you want your code to take an action if it gets a particular concrete value. Matching named variables. Named variables are irrefutable patterns that match any value, and we've used them many times in this book. However, there is a complication when you use named variables in match expressions because match starts a new scope. Variables declared as part of a pattern inside the match expression will shadow those with the same name outside the match construct, as in the case with all variables. In the listing below, we declare a variable named x with the value sum5 and a variable y with the value 10. We then create a match expression on the value x, look at the patterns in the match arms, and print ln at the end, and try to figure out what the code will print before running the code or reading further. So we need to try to figure out what it's going to print. So let's do this. This is called matching named variables. So we'll create a new function, matching named variables. We're going to have let x equals sum5. So we know that at sum 5. We're going to let y equal, this is irrefutable, right? This might be 2, but let's see. Match x. So if it's sum 50, it's going to print ln. Got 50. It's not going to do that, right? 'Cause it's not 50. Sum y. We're going to call print ln matched, comma, y equals, and then we're using the debug trait here, comma, y. And then the catch-all is going to just print ln at the end x equals comma y equals, and we'll pass x comma y. So let's see, what would this be? What would be happening here? Oh, what did it say here? So x equals sum 5, y equals 10. So if we're going to match on x equals sum and then a number. This is going to destructure it. Print ln matched. Maybe. Will this work? I think so, because I think it's a new block. Let's see. Let's walk through what happens when the match expression runs. The pattern in the first match arm doesn't match the defined value of x, so the code continues. The pattern in the second match arm introduces a new variable named y that will match any value inside a sum value. Because we're in a new scope inside the match expression, this is a new y variable. Yep, so I was right. There we go. Of course. Come on. We're on chapter 18. We can't be wrong anymore at this point, right? Not the y declared at the beginning with the value 10. This new y binding will match any value inside a sum, which is what we have in x. Therefore, this new y binds to the inner value of the sum in x. The value is 5, so the expression for that arm executes and prints matched y equals 5. If x had been none value instead of sum 5, the patterns in the first two arms wouldn't have matched, and so we'd fall back on that final parameter. We didn't introduce the x variable in the pattern of the underscore arm, so the x in the expression is still the outer x that hasn't been shadowed. In this hypothetical case, the match would print default case x equals none. When the match expression is done, its scope ends, and so does the scope of the inner y, and that last print ln statement produces at the end x equals sum 5, y equals 10. To create a match expression that compares the value of x and y, rather than introducing a shadow variable, we would need to use a match guard conditional instead. We'll talk about pattern matching guards later in extra conditionals with match guards section. Multiple patterns. In match expressions, you can match multiple patterns using the pipe syntax, like the vertical bar, which means or. For example, the following code matches the value of x against the match arms. The first arm, which has an option, the first of which has an or option, meaning if the value x matches either of the values in that arm, the arm's code will run. So let's try that. Function multiple patterns, let x equal 1, match x 1 or 2, print ln 1 or 2, 3, print ln 3, underscore, print ln anything. This code prints 1 or 2, so it's an or. That's pretty great. Matching ranges of values with ... equals. The ... equals syntax allows us to match an inclusive range of values. In the following code, when a pattern matches any of the values within the range, the arm will execute. All right, let's do that. That sounds cool. We haven't used this yet. Function matching ranges of values. And so we have let x equal 5, match on x, 1 ... equals 5, so 1 to 5 there, I guess. Print ln 1, I don't know, 1 through 5. Otherwise, we'll print ln something else. If x is 1, 2, 3, 4, or 5, the first arm will match. The syntax is more convenient than using the or operator to express the same idea. Instead of 1 dot dot equals 5, we would have to specify 1, 2, 3, 4, 5 if we use the pipe. Specifying a range is much shorter, especially if we want to match, say, any number between 1 and 1000. Yeah, for sure. Ranges are only allowed with numeric values or character values because the compiler checks that a range isn't empty at compile time. The only types for which Rust can tell if a range is empty or not are character and numerical values. Here's an example using ranges of character values. All right, so I'm going to try this here. Let x equal c. So we can shadow. This is shadowing, right? We're shadowing x, so we're allowed to do this here. Match, just gotta put this on it. Match x a dot 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 equals j, so a through j. We're gonna print ln early ASCII letter. That. This is gonna be k, this will be z, and we're gonna change this to late. Otherwise, we're gonna copy this something else, right? Pretty cool. Rust can tell that C is within the first pattern range and prints early access limit. Destructuring to break apart values. We can also use patterns to destructure structs, enums, tuples, and references to use different patterns of these values. Let's walk through each value. Destructuring structs. The listing below shows a point struct with two fields, x and y, that we can break apart using a pattern with a let statement. So let's create another function here. Scroll down. Function destructuring structs. And so here we're going to say struct point x is a signed 32-bit integer, y is a signed 32-bit integer. And in our function here, we're going to say let p equal point, x is 0, y is 7. All right, let point x a comma y b equal p. Assert equal 0 comma a and 7 to b. So what are we doing here? The code creates the variables a and b that match the values of x and y fields of the p struct. So we had this structure here, x and y, and we destructure x into a and we destructure y into b during this pattern here. And that's why these will be equal. This example shows that the names of the variables in the pattern don't have to match the field names of the struct, but it's common to want the variable names to match the field names to make it easier to remember which variables came from which fields. Pretty cool. Because having variable names match the fields, one sec. Because having variable names match the field is common, and because writing let point x equal x, y equals y equals p contains a lot of duplication, there's a shorthand for this pattern that matches struct fields. You only need to list the name of the struct field and the variable created from the pattern. You will have the same names. So in the listing below shows code that behaves the same way as the code above, but the variables created in the let pattern are x, y instead of a, b. So this is very similar to something we'd see in JavaScript. With destructuring, right? We have something very similar. We could say let points equal x comma y equal p, and that would be totally fine. So we can say use the below if we want to change the name of the destructured values, and then here we can say cool. This code creates variables x, y, and matches the x and y fields to the p variable. The outcome is that the variables x and y contain the values from the p struct. We can also destruct with literal values as part of the struct pattern rather than creating variables for all fields. Doing so allows us to test some of the fields for particular values while creating variables to destructure the other fields. So the listing below shows a match expression that separates point values into 3 cases. Points that lie directly on the x-axis, which is true when y equals 0, on the y-axis, x equals 0, or neither. So let's do this. Let p equal point, and we're going to have an x 0, y 7. Again. Oh, we can use the same point. We can just do another match here. Match p point x comma y 0. So we're specifying if this is the case, we're going to print ln on the x-axis at x. When this is 0 and this we don't care about, right? We just care about this. We say it's on the y-axis at y. And then if it's anything else, right? Where we just have an x and a y, then we can say on neither axis. And then we're printing out x and y. The first arm will match any point that lies on x-axis by specifying that the y field matches if it is on 0, and vice versa for the other match case. So we're able to actually match on these exact values. In the example, the value p matches the second arm by virtue of x containing 0, so this code will print out on the y-axis at 7. Destructuring enums. We've destructured enums earlier in the book during our coin example, right? One detail we haven't mentioned explicitly is that the pattern to destructure an enum should correspond to the way the data stored within the enum is defined. For example, in listing 1815, we use the message enum from listing 6.2 and write a match with patterns that will destructure each inner value. So here was something from our old message code. So I'm going to create a function for that. Create that here. Function destructuring enums. I'm just going to copy this because if you remember, we actually had this code somewhere. All right. All right, and then we have a match on this message. So, well, here, let's move this out. We got to move this out. Move that out here. Oh. Let's do this. All right, so we're going to have our message equal message change color 0 160 255, and then we're going to match on that message. Oh, sorry, you can't see any of that. There we go. I'm just copying over what's over here. We're going to match on that message, and if we get message quits, we're going to print this. I'm just going to copy this so we don't get too caught up here, and we'll go over it. So we have message quit. We're going to print ln. The quit variant has no data to destructure, right? Because quit, you can see here, quit has no data to destructure. Move in the direction x and y, so we're able to destructure that value there. Write, where we get the text out of that string, and change color, where we'll get that tuple, right? With the 3. This code will change the color to red 0, green 160, and blue 55, and that's because we have this, right? So it'll go to this branch. Try changing the value message to see the code from the other arms run. So we could, let's call this here in our main function. Let's go ahead and call it. We'll do cargo run. And you can see that arm here change color red. So if we want to see the other arms run, sorry, my eyes are getting dried out here. If we want to see the other arms run, we can just modify our message. So let's comment that out. We'll try message equals right. And right takes a string, right? So what we'll do is we'll do string new. What is this saying? String type is most common string. Yeah, I know that. Expected 0 arguments found 1. Takes a string, right? String new. Hello. Maybe it just wants string slice. No, yeah, it needs to be a string. String new. What's going on here? I guess I could do dot to string. Am I doing string new wrong? Yeah, what's wrong with my string new syntax? Oh, it's string from. Ah, I'm so silly. So silly. I always forget. It's string from that I want. Got it, because it takes 0 argument. String new is an empty string. All right, so string from. So there we go. So now we should get this branch. Text message. Let's try running it. Text message, hello. So that worked. Pretty good. All right, let's go over here. So that's pretty cool. We have the different versions. Destructuring nested structs and enums. Until now, all our examples have been matching structs or enums that were one level deep. Matching, sorry, my contact's getting all messed up. Matching can work on nested items too. For example, we can refactor the code below to support RGB and HSV colors in the change color message. So let's try that. So let's create a new struct called color like they have here. Color, RGB, red, green, blue, 32. That'll give us up to 255, right? So that works. HSV, I guess hex. I32, I32. My eye. Color, and so here our change color is going to take a color. And so what we can do is our color here is going to be change color, and we're gonna actually have a color RGB or HSV in this case, HSV of that. And then we can have our branch change color. We're gonna have two different ones. We're gonna have, oh, sorry, I'm in the way again. We're gonna have our first one. We're just gonna match what they have here. So we have our color, change color, it's an HSV. In our change color here, we're gonna try to destructure it. So our first one, what we'll do is we'll try to grab color, RGB, RGB. And if that's the case, we're gonna have RGB to print out here. Otherwise, if the color, so let's do, if the color is of type color HSV, and we want to grab HSV, here we're going to do HRSRV. And it's actually hue, saturation, and value. And so this is complaining, it's saying unexpected comma. Did I do something wrong? Oh, I forgot a comma. There we go. So that's pretty cool. The pattern of the first arm in the match expression matches message change color enum variant that contains color RGB variant. The pattern binds to the inner value, right? So we're able to grab those. So that's pretty cool. Destructuring structs and tuples. We can mix, match, and nest destructuring patterns in even more complex ways. The following example shows a complicated destructure where we nest structs and tuples inside a tuple and a destructure all primitive values out. Whoa. All right, let's try that. That's pretty cool. Let's create a new function here. Function. We're going to call it destructure structs and tuples. Let's just copy this. This is crazy. And then we'll see what's going on here. So I'm going to make it like a little bit. We'll just go over the one on the right. It's easier to see. This code lets us break complex types into their component parts so we can use the values we're interested in separately. Destructuring with patterns is a convenient way to use pieces of value, such as the value from each field in a struct separately from each other. So here we have all these different pieces here. We have this tuple here and this point, and we're actually able to pick out each part. So that's pretty cool. Ignoring values in a pattern. You've seen that it's sometimes useful to ignore values in a pattern, such as in the last arm of a match, to get a catch-all that doesn't actually do anything but doesn't account for all remaining possibility values. So it accounts for all possible values, doesn't do anything. There are a few ways to ignore the entire values or parts of values using a pattern. So we can use the underscore pattern, which we've already seen. Using the underscore pattern with another pattern, using a name that starts with an underscore, or using ... to ignore remaining parts of a value. Let's explore how and why to use each of these patterns. Ignoring an entire value with underscore. So we've used the underscore here as a wildcard pattern that will match any value but not bind to the value. Although the underscore pattern is especially useful as the last arm in a match expression, we can use it in any pattern, including function parameters as shown in listing 18.7. And so I used this one before, so we won't type that up. This code will completely ignore the value passed as the first argument. 3 will print. This code only uses the parameter y, right? The y parameter. In most cases, when you no longer need a particular function parameter, you would change the signature so it doesn't include the unused parameter. Ignoring a function parameter can be especially useful in some cases. For example, when implementing a trait, when you need a certain type signature, but the function body in your implementation doesn't need one of the parameters. The compiler will then not warn about unused function parameters as it would if you used a name instead. Pretty cool. And this is pretty common. In JavaScript, we prefix things with the underscore in the beginning. That marks it as not being used, so a common thing. Ignoring parts of a value with a nested underscore. We can also use underscore inside another pattern to ignore just part of the value. For example, when we want to test for only part of a value, but have no use for the other parts in the corresponding code we want to run, we see below, it shows code responsible for managing a setting's value. The business requirements are that the user should not be allowed to overwrite an existing customization of a setting, but can unset the setting and give it a value if it's currently unset. So you can see here we have mutable setting value, new setting value, some, we don't care what it is, we just want to do something with it, right? Or the fallback. So pretty cool. This code will print can't overwrite an existing customized value, and then setting is sum5. In the first match arm, we don't need to match on or use the values inside either sum variant, but we do need to test for the case when setting value and new setting value are the same variant, are the sum variant. In that case, we print why we're not changing setting value, and it doesn't get changed, right? So pretty cool. In all other cases, if either setting value or new setting value are none expressed by the underscore pattern in the second arm, we want to allow new setting value to become setting value. We can also use underscore in multiple places with one pattern to ignore particular values. The listing below shows an example of ignoring the second and fourth values in a tuple of 5 items. And we've seen this. Ignoring an unused variable by starting its name with underscore. If you create a variable but don't use it anymore, Rust will usually issue a warning. We've seen that, right? That could be a bug. But sometimes it's useful to create a variable you won't use yet, such as when you're prototyping or just starting out a project. In this situation, you can tell Rust not to warn you about the unused variable by starting the name of the variable with an underscore. Pretty straightforward. Note that there is a subtle difference between using an only underscore and using a name that starts with an underscore. the underscore name syntax still binds the values of the variable, whereas underscore doesn't bind at all. To show a case where the distinction matters, check out below. S some string from hello, put some S found a string, and then we debug it. We'll receive an error because the S value will still be moved into S underscore S, which prevents us from using S again. However, using the underscore by itself doesn't ever bind to the value. So this one will compile without any errors because S doesn't get moved. Ignoring remaining parts of a value with dot dot. With values that have many parts, we can use the dot dot syntax to use only a few parts and ignore the rest, avoiding the need to list underscores for each ignored value. The dot dot pattern ignores any parts of the value that we haven't explicitly matched in the rest of the pattern. In the listing below, we have a point struct that holds a coordinate in three-dimensional space. In the match expression, we want to operate only on the x coordinate and ignore the values in the y and z fields. So here we have a point, origin, match on origin. We only care about the first one. So another similar destructuring pattern, right? We'll list the value x and then we'll just include dot dot. This is quicker than having to list x, y, underscore, and so forth, particularly when we're working with structs that have lots of fields in situations where only one or two fields are relevant. The syntax dot dot will expand to as many values as it needs to be. It shows how to use it with a tuple. So if we have a tuple with all these values, we can do first dot dot last. This is powerful. This lets us get right to the point, first and last. In this code, the first and last value are matched. Oh wait, actually, I do want to copy this aspect really quick. So I'm going to create another function, ignoring remaining parts. So I think this will kind of showcase it a little bit. So you can see here, we have let numbers, and we're able to ignore parts of it. That's pretty cool. In this code, the first and last value are matched with first and last. The dot dot will match and ignore everything in the middle. However, using dot dot must be unambiguous. If it's unclear which values are intended to be matching the dot dot, it will cause an error. So here it's unclear how many in the front, how many in the back, right? It's impossible for us to determine how many values in the tuple to ignore before matching and at the end. So that's why that's not going to work. Extra conditionals with match guards. A match guard is an additional if condition specified after the pattern in the match arm that must also match along with the pattern matching. So this is another thing that we have in Elixir. Match guards are useful for expressing more complex ideas than a pattern alone will allow. The condition can use variables created in the pattern. So the listing below shows a match where the first arm has a pattern sum x and also has a match guard. So I'm going to put this here. Function match guards. Let's create this example here. So here we have let num equals sum 4. And we're going to do match on num. And so we're going to say sum x if x is less than 5. In this case it is. We're going to print out println less than 5 and the value. Right? Then we have sum x without the guard clause. I'm just going to print this. And then we have everything else, right? Or the none in this case. If there's none, it's just going to print out the unit type. It's not going to print anything, which printing, again, we're not returning anything here. It's just, that's why the unit type will suffice. This example will print less than 5 for when num is compared to the pattern in the first arm. It matches because sum 4 matches sum x. Then the match guard checks whether the value x is less than 5, and because it is, the first arm is selected. If none had been sum 10 instead, the match guard in the first arm would have been false because 10 is not less than 5. Rust would then go on to the second. So there's no way to express if x is less than 5 condition within a pattern, so the match guard gives us the ability to express this logic. In the listing below, we mentioned that we could, in listing 1811 back up above, we mentioned that we could use match guards to solve our pattern shadowing problem. Recall the new variable was created inside the pattern in the match expression instead of using the variable outside the match. The new variable meant we couldn't test against the value of the outer variable. Listing 1827 shows how we can use a match guard to fix this problem. So we have let x equal sum 5. I'm just going to do another one here. Let x equal sum 5. And here we'll do sum 5. Let y equal 10. And so this is that example from above, right? And we're going to match on x, and we're going to do sum 50. And again, it's not going to be hit this branch, right? This was the weird part, right? Where we're using y here. Well, here we're going to use n instead. If n equals y, then we're going to print ln matched, comma n equals, comma n, and this needs to be a string. Otherwise, we're just going to go ahead and print ln default case x equals, and our debug here x, and that's because it might be sum, right? Something else. And then at the end, we're going to print this. This code will now print default case x equals sum x. The pattern in the second match arm doesn't introduce a new variable y that would shadow the outer y, meaning we can use the outer y in the match guard instead of specifying the pattern as sum y, which would have shadowed the outer y. We specify sum n. This creates a new variable n that doesn't shadow anything because there's no n variable outside of the match. The match guard if n equals y is not a pattern and therefore doesn't introduce new variables. The y is the outer y rather than the new shadowed y, and we can look at the value that has the same value as the outer y by comparing n to y. So basically we're not redefining y in this case now. So y is 10, right? And so only if sum 10 will this print out. You can also use the OR operator, right? So we can use the OR operator in a match guard to specify multiple patterns. The match guard condition will apply to all patterns. Using the listing below shows the precedence of combining a match guard with a pattern that uses the pipe. The important part of this example is that if y match guard applies to 4, 5, and 6, even though it might look like if y only applies to 6. So let's see. So it looks like if y only appears to 6, but it's actually 4, 5, 6, right? Pretty cool. Maybe we can specify that with parentheses. So yeah, you can see here the precedence, right? At bindings. The at operator lets us create a variable that holds a value at the same time we're testing that value to see whether it matches a pattern. And the listing below shows an example where we want to test that a message hello ID field is within range 3 ... equals 7, so in a range from 3 to 7, but we also want to bind the value to the variable. ID variable is what we want to bind it to, so we can use it in the code associated with the arm. We can name this variable ID, the same name as the field, but for this test, we'll use a different name. All right, let's try that. So I'm going to do function. Let's create another thing here. At, can I use the symbol? At bindings. So we have our message here. So this is a different, I'm going to create a different enum here. Other message. It's going to have hello. It's going to have an ID. 32 there. We can move this in here. Let message equal message hello, other message. Other message hello. And we're going to pass it ID 5. Then we're going to match on that, match on message, and our match is going to say message hello, and here ID underscore variable at 3 dot dot equals 7. So this is the entire case here, right? Then we're gonna print ln found an ID in range ID variable, or in this case variable. So what is this doing? Basically it's matching, and it's pattern matching. It's saying I want to destructure this ID as ID variable when it's at range 3 to 7, right? And then here's the same thing, but for range 10 to 12. And here's the default case here, where it's some other value, right? The example we print will print found an ID in range 5. By specifying ID variable app before the range, we're capturing whatever value matched the range while also testing that the value matched the range pattern. For the second arm, where we only have a range specified in the pattern, the code associated with the arm doesn't have a variable that contains an actual value of the ID field. The ID field's value could have been 10, 11, or 12, but the code that goes with that pattern doesn't know which it is. The pattern code isn't available to use the value from the ID field because we haven't saved the ID value in a variable. So that second pattern, we haven't saved it. In the last arm, where we specified, oh, and also the reason this is complaining is because of a comma. And here it's because we used message instead of other message. All right. In the last arm, where we specified a variable with add range, we don't have the value available to use in the arm codes either, right? Because we're not doing it. Summary. Rust patterns are very useful in that they help distinguish between different kinds of data. When used in match expression, Rust ensures your patterns cover every possible value or your program won't compile. Patterns in let statements and function parameters make those constructs more useful, enabling the destructuring of values into smaller parts at the same time as assigning to variables. We can create simpler or complex patterns to suit our needs. Next, for the penultimate chapter of the book, we'll look at some advanced aspects of a variety of Rust features. All right, that is it. We finished chapter 18. Next up, as you heard, is the penultimate episode. And look, we're at exactly 11 p.m. So we're going to end it here. Again, I will be pushing all of this stuff up to the GitHub repo. So check it out. We did it. We beat chapter 18. Chapter 19 is next, the penultimate chapter, followed by 20, the final chapter, building a multi-threaded application. Again, if you join late or you're watching this and you want to catch up and you haven't been able to, check out the YouTube. All the videos are going to be there with the Rustlings exercises that we did, all the chapters. I'm going to have this chapter posted up tomorrow. So we'll have all the chapters there. Now we're going to have all the way up to chapter 18. We came pretty far. We've done all 18 chapters. We've done Rustlings. We are like full Rustations. I'm very excited to build that web app. Again, follow on Twitter if you're interested in getting updates for when I go live. Also, feel free to add comments on YouTube. I've been loving seeing the comments flow in and answering people's questions / seeing the interest in the content. So happy to have that. As always, you can subscribe and like videos. You'll get notifications for when new content gets posted. Shout out again to Steve Klobnik and Carol Nichols for writing this book so we could be here. And that is it for tonight. So again, don't forget we are live. If you're watching on YouTube and you want to check it out live, and so you can answer questions in real time in the chat and participate and hear your name on stream, right? 9 p.m. to 11 p.m. Eastern on twitch.tv/TomMcGurl. Easy to find it. I'll post it if it's not already posted on the YouTube, but twitch.tv/TomMcGurl. That's 9 p.m. to 11 p.m. Eastern. Feel free to hop in the chat. It's fun. You can get involved. It's cool. If not, keep watching on YouTube. You could always fast forward me, watch me at 2x speed, breeze through these 2-hour streams, right? And get through all of the chapters. So I'll catch you next week. We'll be doing chapter 19, the penultimate chapter of the book. We'll see how far we get through that, and should be a lot of fun. So I'll catch you next week. Thank you, everybody, and have a great night.